Hello everyone, I'm Jingxian. Today I present PushID, pushing the range limits of commercial passive RFIDs. This is a joint work with Junbo, Rajarshi, Haojian, and Swarun. RFID tags are widely used in our daily life. For example, in our pocket, our ID card, bus pass, credit card, even the room keys are all RFID technologies. We also attach RFIDs to packages and products in factories and warehouses. For example, we can efficiently log all the information of the packages by passing them through a RFID reader checkpoint. We also use multiple RFID readers at the checkout of cashierless store to provide automatic payment. Similarly, we also use RFID tags in the airports to eliminate the mishandling baggage in the airports. For example, there are multiple RFID readers in the airport to track RFID tag bags from check-in to check-out. However, millions of RFID tag baggage are still lost in the airport each year. The fundamental reason is that the RFID tag can be only detected at a specific checkpoint in the vicinity of one RFID reader. This is also true for all other cases in the factories and the cashierless store, that the RFID tag can be only detected around individual reader. The fundamental reason is that the RFID system have very short communication range from 5 to 10 meters. The reason is twofold. First, there is no battery in the RFID tag, which means the RFID tag needs to fully rely on the wireless energy transmitted by the nearby RFID reader. And also, we cannot transmit too much power from the RFID reader that can hurt people. So how can we extend the communication range of RFID system today? There are two main methods. They either modify the RFID tag or modified RFID readers. To modify the RFID tags, one of the approach is to basically attach the battery and use better performance hardware in the RFID tag. However, this method makes the RFID tags bulky, limited by battery life, and also add more cost. Another method to extend the range is from RFID reader side. For example, past work used multiple co-located RFID readers to focus the wireless energy towards a particular direction, like a direction signal. However, direction signal is vulnerable to obstacles, and it is sensitive to various orientation of the tags, because most of the tags has polarized antenna, which means the tags need to face where the readers are located to respond. And also, we cannot transmit too much energy to a particular direction that can hurt people. So we present a new system, PushID, which achieves 8 times improvement in the communication range compared to commercial RFID systems. Compared to prior work, PushID extends the range without modifying the hardware, and also PushID is robust in various tag locations and orientations. The key idea of PushID is to exploit the collaboration between distributed readers in the existing infrastructure. For example, we use multiple RFID readers in the airport to track the RFID tag bags. However, now there are many blind spots that the RFID tag cannot be detected, because right now the tag signal is only processed independently by individual reader, which means the RFID tags are either within the range of one RFID reader or not. In PushID in construct, the tag signal is not only listened to by one RFID reader, it's listened to by all RFID readers in the environment. Particularly, now all RFID readers try collaboratively to discover the RFID tags in the environment. We show that this, in effect, expand the RFID tag range to a significant larger area instead of just few zones around individual readers. To see how, let's first have a little bit background about distributed beamforming. The goal of beamforming is to focus the wireless energy towards a particular point. Specifically, let's assume there are 4 transmitters transmit the same signal in the air. At the center red point, this signal can add up constructively reinforce each other, or add up destructively cancel out each other. What the beamforming does is to pre-multiply the signal of all transmitters by some set beamforming ways, so that the energy can always add up constructively at the center red point. Also, using more readers, we can add up more energy at the center red point. Theoretically, we can get a transmitter gain that's proportional to the log of the number of readers we use. Notice that the constructive signal can also happen bidirectionally, which means we can use the same set of beamforming ways to amplify the reflected signal at the center red point with a receiver gain that's proportional to the log of number of readers we use. So now, to do distributed beamforming, one of the most important decisions we need to make is to figure out what the beamforming ways are. And also notice that we have no knowledge about the RFID tags in the environment. We don't know if they are existing or where the tag is. So we also need to power as many as possible RFID tags at various unknown locations. So how do we get the beamforming ways in traditional distributed beamforming? Since we are the first distributed system for RFIDs, let's look at a very related context which already exists, which is Wi-Fi. The technique we can get in the beamforming ways is called channel reciprocity. Basically, if we want to beamform energy to a Wi-Fi-based client, which is a Wi-Fi-based cell phone in this figure, the first thing we need to do is to ask this cell phone to transmit some signal. And the routers measure this signal and infer the beamforming ways and apply it to downstream to beam maximize power to this Wi-Fi-based cell phone. But let's switch to our context if there is an RFID tag we want to beamform to. Based on channel reciprocity, the first thing we want to do is to ask this tag to transmit something. However, there is no energy for this tag. There is no battery. That is, before transmitting anything from the tag, we need beam energy to this tag from the readers. However, to beamform energy to this tag from the readers need a response from the tag because we don't know if they exist and we don't know where the tag is. So this is a chicken-eyed problem in our context that we cannot directly use channel reciprocity in our RFID context. So can we just naively iterate over all possible beamformers that hopefully we can get some response from the RFID tags at unknown locations? However, it takes time. It takes 26 hours in a small reference room. To resolve this dilemma, we present PushID that develops a novel blend distributed beamforming. Our goal of blend distributed beamforming is to discover all RFID tags at unknown locations over a given geographic region. Based on this goal, instead of iterating over all beamformers randomly, let's look at our space of interest and divide it into a grid of individual points. Now, let's beamform the energy to every individual point in the space, one point at a time, and finally, discover all RFID tags in our desired area. For example, let's use this set of beamforming ways to beam the energy to the center red point. We may think about this: if we focus the energy to the individual point, the energy should only at the individual point, and everywhere else should have no energy. However, things are more complicated because radio signal can constructively and destructively interference in the air with each other. So PushID first models the received signal's power at each point in the space by applying this set of beamforming ways. In this figure, we use yellow to represent high received signal power. We do see the highest peak is at the center, but we also notice that there are multiple yellow peaks that's around the center with similar received signal power, which means we can use one beamformer to activate many RFID tags at the same time instead of just the tag at the center red point. Let's take a further look of these two 2D energy distribution by applying two beamformers. In this figure, we also use yellow to represent high received signal strength. On the left side, we focus the energy into the center. On the right side, we focus the energy into the individual point within the black circle. Overall, these two energy distributions looks quite different. But let's look at these regions within the green blocks. Actually, they looks similar, which means even though we are focusing the energy to different individual points, but some paths that are overlapped in the desired space, which means integrating all beamformers to focus individual points would lead to much overlap and efficiency. Based on this observation, PushID first minimizes overlap between energy patterns of beamformer vectors it applies. To rephrase this problem, we can conclude that PushID first finds the smallest number of beamformers among n beamformers, so that we can provide sufficient energy to every individual point in our desired area. Actually, this is similar to a problem in computer theory called set cover problem that aims to find the smallest number of sets among n sets, whose unit is precisely the universal set. So we modified the set cover problem into our energy coverage optimization. I will not go too much detail here in my talk, but this is a well-known NP-complete problem that we use a heuristic approximation to resolve this. But notice that the complexity of this optimization problem is highly dependent on the number of beamformer candidates, which is the size of the search space of this optimization. So to improve efficiency, we must reduce the search space of beamformers. To do this, let's take another look of these two energy distribution. Specifically, let's focus the regions within the green blocks. On the left side, we focus the energy into the center. That's why we saw the yellow regions is located at the center. On the right side, we apply a small phase perturbation in the beamforming vectors that we saw the yellow region actually is spreading out into a wider area, which is good in our context because more RFID tags has the possibility to be activated. However, diffused energy too much would also make the energy per unit may not be larger than the threshold to activate the RFID tags. So PushID need to select the beamformers between these two extremes, that the beamformers not focus the energy too much and not diffuse energy too flat. We need to select beamformers within the Goldilocks zone that are just right, maximizing the area over energy threshold. Based on this observation, PushID must favor beamforming ways with maximal total area where RFID tags remain powered. To resolve this, we use a gradient-based approach to prune the search space. Basically, we generate n beamformers randomly and refine beamformers with maximized coverage area using gradient approach and feed the new beamformers into search space. So now we have our PushID that can efficiently discover all RFID tags at unknown locations over a given geographic region. PushID to do this, we first minimize the overlap of the energy patterns of the beamforming ways that we how formulate a set cover problem. And to improve the efficiency, we use a gradient-based approach to prune the search space. In this animation, we show how the energized area is accumulated by applying the beamformers from the optimal set generated by the PushID algorithm. Besides developing a novel blend distributed beamforming, in the system design, we also account for multipaths because in reality, the reading environment is more complex and dynamic. And also to ensure the collaboration between the distributed readers, we also develop a spanning tree-based approach to do the synchronization. Please see the details in our paper. Let's go through our evaluation part. In our implementation, we use commercial passive RFIDs that just cost 1 cent. We use USRP as our PushID readers. We compare PushID to multi-attendant MIMO and closest reader baselines. Multi-attendant MIMO, we assume the readers are collocated. Closest reader, we assume the tag signal is only decoded by individual reader. We deploy our system in LAN offset and non-LAN offset radio environment, both in the football field and office area. We also try some mobility tests that the tags moves at a working speed. Let's see our first result, range performance. Overall, PushID achieves a communication range of 64 meters, which is 8 times improvement in the communication range compared to commercial RFID systems. In this figure, we saw the closest reader performance is almost flat, around 9 meters. Notice that sometimes multi-antenna MIMO approach outperforms than PushID, when the RFID tags are really facing to the antennas of co-located readers. But overall, PushID achieves a higher average range performance than other two schemes because PushID leverages the distributed readers to give us a richer spatial diversity. We also evaluate the impact of tag orientation using throughput. Basically, we model the distribution of throughput of one RFID tag. And this tag is progressively oriented along various directions at 100 locations. In this figure, we get a better performance in the throughput, which means PushID is more robust in various tag orientations. We also evaluate the coverage performance of PushID, given a geographic region, which is 60 by 60 meter area. In this figure, when we increase the number of beamforming vectors, we discover more RFID tags in the environment. We use 980 beamformers to discover over 95% RFID tags in the environment, which just take 4.4 seconds. We also notice that there is diminishing returns after we discovering over 95% RFID tags, because the last 5% RFID tags are at poorly oriented and suffering extreme shadowing. But we claim this as one of the limitations for our PushID algorithm. But I think this is also true for all other cases in the various system for RFIDs that we cannot deal with every extreme cases in reality. We also have more evaluations. Please check it out in our paper. To conclude my talk, we present PushID, the first distributed system to power commercial passive RFID tags. We developed a novel blend distributed beamforming to efficiently discover RFID tags over a given geographic region. We achieved 8 times improvement in communication range compared to commercial RFID systems. Thank you very much. I'm very happy to take any questions.
Questions? Kyle.
Hi.
Hi.
Nice talk. So the design of your system is that you model the wireless propagation, and then you do a set cover on the result of that.
Yes.
So this seems to really, really crucially depend on the multipath.
Yes.
So
Mm-hmm.
I understand you highlighted it in your talk, but can you go into more detail about how the multipath compensation works?
Yes. We do consider the multipath in the radio environment. So now I can give you a very high level idea. So basically, first we have a given geographic region. We have desired area that we want to discover the RFID tags in the environment. So based on this, we first get an initial optimal size based on PushID algorithm. And then when we apply the beamformers in the environment, we progressively get the response from the RFID tags. And use the response, we can infer the multipath characteristic based on this. And then we locate the reflectors in the radio environment and add this to our PushID algorithm. Yeah.
Thank you.
Thank you.
Hey, great talk. So a typical RFID reader uses like a patch antenna, so it has high gain to talk to the device. So I presume you're switching to an omnidirectional antenna. And is there any sort of sacrifice you're making in that if a device's RFID tag is very close to the tag, close to this close to the Omni reader, is it less likely now, because it's an Omni antenna, if the rest of your system fails, that one antenna won't be able to read from that tag anymore? Because it's not a high gain antenna anymore to talk to the tag.
So Yeah, so if the tag is so close to the antenna, so there could be near field effect for these tags. Actually, it's like a near field communication, not a far field communication anymore. Yeah.
Okay. So you're saying in near field it might still perform quite well.
Yes. Yes. Yeah.
Thank you.
Thanks. Yeah.
Hi, Longfei from Microsoft. So I have a question about your beamforming part. So based on my understanding, like the width, the radius of your beamforming spot is actually determined by the layout of your distributed antenna array, right?
That's right.
And also the number of the antennas. So my question here is do you have any idea about the optimal settings for this kind of layout or number of antennas? Yeah.
Yes. So before PushID, we all consider using like multiple collocated readers to extend the range, or just one readers to just query the tags within the range.
Yeah.
And now we have PushID, a distributed system that now we want to leverage the distributed readers in the existing infrastructure, like in the airport. There are multiple readers, right?
Yeah.
So now we have our PushID system, distributed system. We also can think about what is the optimal deployment of the distributed readers to get the to discover all of the tags in this given geographic region. Yeah. So we don't explore this design space in our paper, but I think this is a really good direction to work on this. Yeah.
Okay, thank you.
Thank you so much. Yeah.
Let's thank Jingxian once again.